Welcome back to PLS 510. Today we want to take up the first part of our series on understanding forage quality. We're going to start with the definition, and it's important to keep this definition in mind because we will spend the bulk of our time talking about indirect ways to measure forage quality, but the most direct way is to measure the ability of a forage to support a desired level of animal performance. The best way to know how much gain a ton of hay will provide is to feed that hay to your desired animal and then weigh them at the beginning and weigh them at the end. But this is totally non-useful. It's like knowing the basketball score the day after the game was played. You're 100% accurate, but the information does you no good. So we're going to move into more about forage quality. Now, we will talk a lot about chemistry, but I want to first start off again. We got the definition. Now we're going to talk about appearance, because appearance matters, particularly in hay that is being sold. And we call these characteristics, these appearance characteristics, organoleptic characteristics. First and foremost, the color matters. Green color is certainly appealing, but it's also an indication of some positive things like quick curing, lack of rain, and in Kentucky, lack of being sun bleached due to the presence of dew. Now, the smell also is something that we can sense. We want it to smell fresh. We want it to have a sweet smell. We don't want to have it smell musty, because that's an indication of mold. And we like soft textured hays, and we know that on the extreme end, hays that have like foxtail with heads, that head itself can cause us difficulty. So we like that soft textured hay like we see with orchard grass. There are other factors, and you could list several here, but I'm going to list leafiness, freedom from mold, which is also related to smell, and no obvious foreign material or toxic plants. It's important to know that good hay is not always green, like this alfalfa hay from Fleming County, where the bales had been sitting on a wagon in the edge of a barn, where the sun could bleach the ends of the bales. And you can see that on the inside, the bales are quite green, but on the outside look, at least based on color, not very appealing. And that's why we test, because a forage test is going to look past the surface and reveal the nutritive quality, or at least help us attempt to predict the nutritive quality, which is, of course, the ability to support performance. Now, I want to begin to contrast this idea of what we want to know versus what we measure. We want to know how well an animal will perform from a given forage, but what we measure are components, and then based on research, we will predict performance. For example, we will measure percent nitrogen and estimate protein from the general proportion of nitrogen within protein that we find in plants. We measure fiber, and then we estimate intake and energy from fiber. And here's the first time you've seen these two terms, neutral detergent fiber, or NDF, and the subset of neutral detergent fiber called acid detergent fiber, or ADF, and we will talk a great deal more about these. Looking further into the nutritional components of a forage, the protein is the most costly nutrient to buy if you're going to go buy a supplement. 16% horse feed costs more than 12% horse feed, and that's referring to the protein. So we intuitively know that protein has value. But the interesting thing, and the thing to really keep in mind with forages, is that protein is the nutrient that is easiest to supply with forage crops. So we want to coach ourselves and to look past protein deeper into the analysis to find out how good the hay really is, or the forage really is. We want to go dig deeper and find out about the energy, or which is synonymous with digestibility. Energy is the most limiting nutrients for performance for horses, for cattle, for sheep, for goats. But it's the most difficult to measure and understand. And as I told you, we measure fiber. This energy nutrient or energy component is inversely related to fiber. High fiber, low energy. And other things that we may want to know about are the minerals that are present in forage, and also if we're talking about baleage, we would like to know pH, or the acidity, and the relative amounts, or the absolute amounts of volatile fatty acids, such as lactic acid, acetic acid, and so on. Now, my very best analogy to understand nutritive quality in plants as far as a ruminant goes is the liquid center gum analogy. And so you remember liquid center gums, I hope you do anyway. It was something that certainly I knew growing up. And you would buy the gum, you put it in your mouth and you'd bite into it, and the liquid center would burst out, right? And it was very sweet, and it lasted a short while, and then you would chew on the gum and it would last longer, and you would chew and extract the sugar from the gum, and then you throw it away. This liquid center is just like the cell contents. The cell contents inside of the cell wall, think of a square, they're 100% digestible. They're composed of soluble carbohydrates, protein, all of the working molecules within that cell. And that middle of the cell could constitute 30 to 60% of the dry matter. The chewy outside of this gum is like the cell wall. It provides it's somewhat digestible in the rumen or the cecum colon. It releases sugar from the action of the cecum or colon, like we release sugar when we chew. And the cell wall can comprise 40 to 70% of the dry matter within a forage. Going a little further, and we try to visualize this in terms of relate that plant cell to fiber and fiber digestibility. The chewy outside, as we said, is the same as the total cell wall. Now, this is the first time we equate something in the cell to a forage analysis. The total cell wall is the same as neutral detergent fiber, or NDF. It is somewhat digestible depending on maturity. And to me, this is one of the most difficult concepts to understand. We kind of understand the difference between sugar water and shredded wheat, and I'll use that analogy a bit in a second. But the chewy outside is like the cell wall. When the cell is and the plant is immature, then there's a lot of sugar in the cell wall. Yes, it's still a cell wall. You gotta be able to break it down to get the sugar. But it's young. It's not stiff and old and decrepit like you can think of people in that ways. But that's the cell wall. That's the NDF. And just like we chew the gum and we extract the sugar out of the gum, the fiber from the mature plant is like old gum, or ADF is like old gum. It's lost its sweetness or digestibility, and it's tough due to changes that come with maturity. So when we're done chewing the gum and we've extracted the sugar, just think of that as ADF, acid detergent fiber, or the relatively indigestible part of the forage cell. So I'm going to restate what I just told you. Chewing the chewy outside before chewing is the total cell wall, the NDF, the neutral detergent fiber. The gum left after chewing is similar to acid detergent fiber. So it's always important to know that acid detergent fiber is a subset of NDF. That means acid detergent fiber is less than neutral detergent fiber in every case with forage crops. Yeah, ADFs is a subset of NDF. So just to put it on a slide and kind of put it here all in front of you at one time, the main fiber terms that you'll see on a forage analysis are going to be NDF, neutral detergent fiber, total fiber in the plant. It's composed of cellulose, hemicellulose, and lignin, and we use that number to predict intake. ADF, acid detergent fiber, is a subset of NDF, and it's composed of cellulose and lignin. And right away, you can see by difference here that if we need to know the amount of hemicellulose in a forage, then if we subtract ADF from NDF, then what we have is hemicellulose. And so we use the ADF then to predict TDN, total digestible nutrients, and we're going to use a lot of terms synonymously here: energy, digestibility, total digestible nutrients, or TDN. And we're going to think of them in the generic sense most of the time as just the energy value of a forage. Now, we do use ADF in the prediction of TDN, but the methods vary greatly. And when I say that, I'm saying that laboratories, individual laboratories, will most likely use different equations for calculating TDN. Now, a good test starts with a good hay sample, and there's more error associated with defining the quality of hay in taking the sample probably than anything else. And so we want the sample to be representative of the group of hay. We call that a lot of hay, which is hay from one field harvested and stored alike. We want 15 to 20 core samples, or enough that we feel like we've sampled a significant number of bales within that lot. And we want to send the whole sample to the lab. We don't want to separate that sample and split it and separate it and send it to two different labs and then compare the labs, because there's a lot of error with splitting a sample that masks any difference between two labs. Now, I know from surveys and just formal and informal that it is not common for people to test their hay. And why is that? And it's interesting scenarios, and you can imagine scenarios in your mind why they don't test. It's trouble. It's takes time, and I don't have a probe, and well, the hay is back in the back of the barn, I can't get to it, but and another reason is I think people think that hey, I know my hay is bad, why should I pay someone to tell me my hay is bad? Or like this, it's just cow hay, why should, it's nothing special, I don't need to get a test for cow hay. Well, I'd like you to think that in this case, that's especially why you need to get a hay test, because there are really, really few bad hays, but there are plenty of bad diets. And the thing that we don't want to happen is to have a bad hay and not know it, and to feed it to something expecting performance and not get it. Now, we want to use a quality laboratory, and this happens to be the Kentucky Department of Agriculture's hay test report. But on their website, they've got this certification sticker or stamp from the National Forage Testing Association. They're certified for estimating dry matter, protein, ADF, and NDF. So we want to use a quality laboratory. Now, there are two main ways to estimate forage quality. Wet chemistry, which is direct, it's slower, it's more expensive, and it's destructive in that it consumes the sample as we send it off for we process it in the lab. Now, near-infrared reflectance spectroscopy uses light to scan finely ground forage and then collect the reflection of near-infrared wavelengths that hit the surface of the forage. This is the near-infrared method has been practiced since, I'd say, the 1970s. It's calibrated with wet chemistry. It's non-destructive, it's quick, and it's less expensive in that we can have many predictions or a lot of data from only one scan. Now, if you're thinking of and we do this a lot, we think, should we get a, we use, or NIR is used for about 90% of all samples that get tested, but should we use wet chemistry? If we think that the sample we are testing does not exist, or we fear that there's no samples like it in the calibration set for NIR, then wet chemistry might be helpful. If we have unusual results with NIR, then we will send them off for wet chemistry to confirm what we think we know. And make that point again, your sample type must be represented in the calibration set. Now I want to draw this introductory part to a close, reminding you that the best measure of forage quality is animal performance. We want to be able to predict it, and so we will then measure things like protein and fiber, and then use that to predict animal performance. In our next lecture, we will talk about understanding forage quality reports. Until next time, we'll see you later.